Hi guys. Today we're going to continue our discussion on chemical kinetics, that is, rates of change among chemical reactions. We'll be talking about the equations that are going to include rate, known as rate laws, and we're going to talk a little bit more about reaction mechanisms. Let's begin discussing mechanisms again. The sequence of elementary steps that make up a complex reaction is a mechanism. Really, we're saying that you can have a first initial step that leads to a second step that leads to a third step. Whatever you begin with in the first step and whatever you end with in the third step, those are the only things that we consider when we write out a normal chemical equation. But it's important that we understand a lot of complex processes do take place in multiple steps. All of the steps, when combined, are known as the mechanism. Each step can be fast or it can be slow, but the overall rate of a reaction is going to depend only on our slowest step. Okay? The slow step is also sometimes called the rate determining step. So if you see that rate determining slow step, that's the thing that we want to focus on as we try to understand the process. To help clarify this idea, I want you to consider two different scenarios. If we have cars that are trying to cross from one side of a river to another, they're going to cross it on a bridge. And let's imagine that there are two stopping points, there are two plazas where the cars have to pass. Well, when you look at this first example, you notice that we have a pileup of cars at Plaza A. That means they're moving very slowly through the plaza. Well, once they cross the plaza, they're going to move very quickly to get into the next area, the next plaza. In this case, notice that there's no pileup. The worker in the toll booth in Plaza B is getting these cars quickly through, so we would say that's the fast step. And if I'm trying to figure out how quickly a car can go from point 1 to point 3, I don't even want to really consider point B. The slow step, and that is, again, point A, that is going to determine the rate at which cars can travel across this bridge. If the second step, right here in Plaza B, is slower, notice that the pileup happens right there. Cars can quickly get from point 1 to point 2 because at Plaza A, we'd say that's the fast step. Once they reach Plaza B, the worker in that toll booth is working more slowly at processing cars and getting them across. So this is our slow step. And if I want to figure out how quickly cars can travel from point 1 to point 3, I focus on the step at Plaza B. Now, let's get into some of the basics about rate laws, rate equations. What we need to do is we need to be able to take those elementary steps, those simple steps, and figure out how rate ties into those steps. We've already said that the slow step is what determines the overall rate of an equation. But now let's talk about rate laws. What are rate laws? Again, rate equation, rate law, they're the same thing. This equation has this general form. You have your rate, which you should be familiar with already, in units of molarity per second in most cases. Next, we have our K, which is a constant. It's specific to a chemical reaction that we're going to be analyzing. Next, we have our capital letters here, our A and B and C. Those are going to represent reactant A, reactant B, reactant C. So it's the identity of whatever things are reacting. In this case, we're showing 3 different reactants coming together. Our exponents here, the X, the Y, and the Z, well, those we refer to as the order of that reactant. And really, it is a power. It's just an exponent. If I'm trying to figure out the rate, if I were to, let's say, take A, and I were to triple it, if I go 3 times as much A, if the order of A is 1, that's going to essentially lead me to having 3 times the rate. If I triple the concentration of A, I triple the speed at which this reaction takes place. If we look at C, and let's say that I'm going to have an order of 2 on Z, well, that means that I take the molarity of C and square it in order to find the rate change. If I were to, let's say, have 4 times the concentration of C, and the order is 2, well, the effect there isn't 4 times the rate, it's going to be 4 times 4, 4 squared. And 4 squared is 16 times the rate in that case. Now once again, just to make sure we have this concept, k is a rate constant. We're going to be looking a lot more in depth at rate constants. The A, B, C shown here are going to represent the different reactants, and because we have those in square brackets, those are in the units of molarity, moles per liter. So focus on that for now. X, Y, and Z, those are going to be typically whole number integers, though they can be fractional. The overall order of a reaction is based upon the individual orders of the reactants. So if I look at this and I see that the order of A is 1, let's say the order of B is 1, and the order of C is 2. The overall order that I'm trying to determine would be the sum of those individual orders. So here, X is 1, Y is 1, Z is 2. That's 1 plus 1 plus 2 makes 4th order overall. A few very, very key ideas that we want to get into when it comes to our rate equation. We want to first focus on the coefficients. A lot of the times we get stuck by looking at the coefficients of the overall reaction and thinking that those have to do with the order of those specific things. But remember that the overall reaction might take place in multiple steps. So the stoichiometric coefficients of the overall reaction do not necessarily predict the order of those reactants. Second idea is, if I look at the coefficients in the slow step, they do predict the order, okay? So we'll talk more in depth about this, but coefficients in the slow step are indicative of the order. If you had 2A plus B makes 3C, for example, if this is the slow step, then we would have a second order with respect to A and first order with respect to B to make third order overall. In the rate equation, we have that constant K, and it's important also that we recall the unit of K can be determined by looking at all the other factors in an equation, and the value can be determined by plugging in numbers. So the unit and the magnitude or the value of a rate constant is very important. Third idea is that a reactant that has no effect, if there's no change based on a reaction, we would say that it's zero order. Typically, zero order will exist when you have a reactant that is required to make a process take place, but it is only seen in a fast step within the mechanism. Remember that if it's in the fast step, it doesn't matter if I double or triple that reactant. It's not going to have any effect on the overall order, because the overall speed of that equation is all about our slow step. Orders can be fractional. In AP Chemistry, really, you're going to primarily be dealing with 0, first, and second order. It can exist, however, that you'll have half orders or 3 halves. You can have fractional orders. And again, these are the exponents. It's based upon the stoichiometry of coefficients in the slow step. In any mechanism, the sum of the individual elementary steps is going to be used to find the overall equation. Now to demonstrate this, if I gave you X turns into Q, and a follow-up step that Q plus Y makes Z, if I were to combine these two equations, we would see that X and Y carry down. But Q, there's one Q on the product and one on the reactant side. So we would leave that out of the overall equation. They cancel themselves out. And Z would then be the only product. So take all of the steps in a mechanism, combine them, and you can add it up to make the overall equation. An intermediate is something that's formed in one step of a mechanism, but it's consumed in another. So if we're going to look here, we can see Q is produced in one step, then it's consumed in another. So we can essentially cancel it out of the overall equation, and we refer to this as an intermediate. The final idea that we want to talk about here is that if you had a substance that's part of a mechanism, it's present in the beginning, it gets used up typically to make intermediates, but then is reformed and it exists as a product, we have a special name for these. This is known as a catalyst. There are multiple kinds of catalysts that we can deal with, but the main thing that we want to emphasize is this. If, let's say we had X plus A makes R, then we have R plus B makes Z, and finally, if we had A plus B turns into X. Think about what's going on here. The first thing is if we wanted to do the overall equation, what we notice is I have X present in the beginning and it's also present in the end. Well, if it's present in the beginning and it's also present in the end, this tells us that it wasn't consumed. It would be identified as a catalyst. Now, some other things that we like to look at here. We have A being used as a reactant in two different steps. So if I'm going to create an overall equation, I would say that there are two A's overall taking place in this. Oh, I'm not sure what happened there. We'll go back to it. There are two A's. Then we can see that R is produced in one step, but then it's consumed in another. So R, we can cancel out. That would be, once again, an intermediate. B, we see happening as a reactant twice. So 2B would be written on the reactant side. And finally, the only product that comes out is a single Z. So hopefully that made some sense. We'll be practicing this a lot more, but intermediates and catalysts, it's important that we can spot them within a mechanism. Now, I'm going to be letting you work through these tasks on your own. I'll give you a couple of additional examples, but take the time to identify your catalyst and intermediate in the mechanism below, and then you'll be able to answer these questions on your own, and we'll discuss them later. In this example, we have a reaction, and it has the following mechanism. Our W plus R, W turns into R. This is the slow rate determining step. R plus Y reacts to form Q, and this is a fast step. Then what we're looking at is Q turning into Z, and that is another fast step. The overall equation is W plus Y makes Z. So the things that I want to highlight are, once again, let's identify some of the specifics here. Since we know the first step is the slow step, that's rate determining. And if I were to create a rate law, what I would need to do is focus on that slow step. W is the only thing acting as a reactant in that slow step. So if I were to create a rate law, it would focus only upon W and nothing else as I'm writing it out. The general form, remember, is that the rate is equal to K times the concentration of relevant reactants raised to whatever power you see as their coefficient. In this case, my coefficient is only a 1, so if it's a 1, that means it's an order 1, and a 1 can essentially be disregarded, right? It doesn't change anything, it's just W itself. So the rate law, once again, is rate equals K times the concentration of W raised to the first power. It's first order with respect to W, and it would be a first order overall reaction. Now, a side thing that we want to emphasize here is, remember, R is produced as one part of a step, and then it's consumed in the next step, which means that I can essentially leave it out of the overall equation. This is known as an intermediate. You also see that Q is produced and then consumed, so Q is also an intermediate. And our overall reaction is W plus Y makes Z. Here we have another example. In this case, our overall reaction is A plus B makes C plus D. Now the mechanism that we're going to put in here is showing a fast initial step followed by a slow rate determining step. Well, something is a little bit different in this situation. Since Q exists as an intermediate, it's an intermediate in the slow step, so we have to consider Q. We have a problem though. The intermediate Q is not actually one of the reactants. It's a byproduct of one of these reactants. What we'd have to do in a situation like this is we need to substitute in A for Q, because the concentration of Q is directly determined by the concentration of A in a 1-to-1 ratio. So if I were to double the concentration of A, it almost immediately doubles the concentration of Q, which is then used up with B in our second step. So if I were to write out a rate log based upon this information, here's what we would think about. A can be substituted for Q, and Q has a coefficient of 1. B also has a coefficient of 1. So the rate law should be written out as K times A to the first times B to the first. Here I'll let you go ahead and work through another of these tasks. Try these ones out, come ready to discuss it. All right, let's move on now into our third example. One of the reactions that we tend to see a lot when we're studying rates is that of our bromate ion, BrO3-, bromide ions, hydrogen, in this case the hydrogen ion that we'd see in an acid. These three items react to form bromine in a liquid state in solution, and we also are going to form water. So the following data is provided just so we can see in a series of different mixtures. So we have 4 mixtures, A, B, C, and D. We've set up our experiment so that some of these things are going to be different. Some of these things are going to be the same. So that actually is very intentional. And in a second, we're going to explain why we chose to keep some things the same while other things are different. But what we'll always be able to do is compare one thing changing to the change to rate. Now, let's begin here. For now, I only want to focus on mixtures A and B. What we're going to see with mixtures A and B is that we go from 0.005 molar to 0.01 molar. That's an increase by a factor of 2. We've doubled the concentration. When we look over at the rate, you'll notice that we go from 10 to 20, which again is 2 times the rate, a doubling factor. But don't forget, we have to think about order when we're talking about rate. If I'm doubling the concentration and I double the rate, that's really 2 raised to the first power. And what that means is we have a first order change with respect to our bromate ion. This is especially important that we note. Most of the time when you're just doing an inspection, when you're just looking at data, you tend to get a little bit lost because of fractions, because the numbers aren't exactly perfect. And that actually is reality. In a lab, your numbers aren't going to be perfect. There are a lot of variables that can get in the way. So do your best to find kind of a sweeping change. What is the difference? What is it closest to? And kind of work from there. Now, we understand that we were first order with respect to bromate. Now, let's take a look at something else that changes. Notice here that the bromate concentration is fixed, and then our hydrogen concentration is fixed. So we want to focus now on bromide, Br-. You'll see here that once again, we are doubling the bromide concentration. And when you compare the rates, we go from a rate of 20 units to a rate of 40 units. So what we're doing is, again, doubling. This shows us that we have 2 to the first power as the change to rate, so it's first order. If I'm doubling the mixture and I double the rate, we have first order change. We would say that this is first order with respect to bromide. Now for our final inspection of our data, we're going to disregard mixtures A and B. Here, notice that in C and D, bromate doesn't change, bromide doesn't change, but we do see a change in hydrogen. In this case, we're going from 0.03 to 0.06, so we're doubling the concentration of the hydrogen ion from the acid. If I'm doubling that, you'll notice that this time I go from 40 to 160. Well, that's not 2 times as much. That's actually going to be 4 times as much. But you got to focus back on the original change. This is a base change of 2. When we're trying to figure out that 4, what we would do is we figure out how many times do you multiply the base in order to come up with the new rate change. Well, 2 raised to the second power is 4. 2 squared is 4. So what we're seeing between 40 and 160 is 2 to the second. This 2, our exponent, is the order. Since I'm doubling the hydrogen ion, the rate is quadrupling. That tells us this must be second order with respect to the hydrogen ion. Now, when I look at all of the changes, what I want you to remember is we said it is first order with respect to bromate, first order with respect to bromide, and second order with respect to hydrogen. So if I were to look at that, the rate is directly proportional to BrO3 minus to the 1, Br minus to the 1, and H plus to the 2. Writing this out as a complete rate law, we would say that the rate is equal to K times bromate times bromide times hydrogen ion squared. Once again, I'll give you a chance to practice these, and then we're going to move on and we're going to talk about how to deal with a mathematical treatment of rate data. Sometimes your numbers aren't very clean and they're not as easy to just spot. So in the mathematical treatment of data, what we're going to do is we're going to find the rate law by looking at 2 of the experiments at a time, canceling out information that we can. So first off, we're looking at experiment 2, experiment 1. The rate of 2 is given as 4 molarity per minute. I'm going to continue with the rate law by saying that is K times 0.1 raised to the A. Now it's an A because I don't know the value. I'm just going to create a variable. That 0.1, once again, refers to our X term, and then our Y term is our 0.025 in experiment number 2. The B is our unknown order. Well, what's nice about this is we can simplify the expressions. If you have any number divided by itself, you know that that ends up being 1. It cancels out. So we can do that by crossing off a couple of values. Here, we can cross off our 0.250 raised to the B with the other 0.250 raised to the B. Also, we'll cross off our K values. Now, we don't know what the values are, but we know that K divided by K, anything divided by itself, will cancel out. Now, what this leaves us with is 4 over 1 must be equal to 0.1 over 0.005, all raised to the A. So we're going to simplify that expression by combining these in parentheses and raising the entire expression on the right to the A power. if I just plug in the numbers there, 0.01 divided by 0.005, you can use a calculator, or if you can see it, notice that this is twice as much. This has to be a value of 2. So we're saying that essentially 4 is equal to 2 raised to the a. Well, the only way to make that statement true is if a equals 2. So the rate is second order with respect to x. I figured out one of my orders. Okay, now we're not quite done. Now that I've figured that one out, I'm going to take a look at experiments 1 and 3. So we're going to go ahead and block one of these off. We'll block off 2 in this case. And look only at 3 and 1. Well, again, what I'm able to do is I can simplify a few things. I know that k divided by k is 1, and I know that 0.005 raised to a and 0.005 raised to a would cancel out also. So in my simplified form, what I have here is 1 over 1 is equal to 0.0125 over 0.0250. Well, that's 1/2, or 0.5 raised to the b. So when I think about that, after we break it all down, well, the only way for us to get 1 out of a 0.5 raised to the b is if the b value is 0. So we must have the y reactant is going to be 0 order. Okay? In this reaction, y is going to be 0 order. Now that I have that data, I can analyze it. I can do more with it. So take some time to work through these problems, and then we're going to go ahead and continue. Just about wrapped up on these ideas, actually. So work through these. Hopefully this all made sense to you, and come ready to answer some questions in class.